Hello, everyone, and welcome to the third day of the LightCon Preview Week. My name is Janina Lorenz, and I am project manager of the LightCon at Deutsche Messe. Today is June 24th, and right now we would have started into the second day of our new International Congress Fair LightCon, the first cross-material and cross-technology platform for lightweight solutions for all industries. We would have if the Corona crisis hadn't forced us to postpone the premiere to next year. Nevertheless, I am very glad that at least today we are able to meet virtually. We have about 100 participants at the moment. That is really awesome, really amazing. We're glad to have you here. And hopefully next year on June 23 and 24, we can all welcome you here in sunny Hanover. For the premiere of LightCon. With the preview week, we want to give you a small foretaste of what LightCon 2021 will be all about in the conference program, but also in the exhibition. So stay curious. And for today, I hope that you will enjoy the webinar. Thank you all for being here with us, and a special thanks to our speaker, Dr. Christian Hamm, for sharing some insights with us today. I would also like to thank our founding partner, Composites United, for the great support in organizing this event. So before we will start, I will give the word to Bastian Brenken from Composites United for some organizational remarks. Thank you.
Good morning, everyone. Also on behalf of Composites United, a warm welcome. We just passed 100 participants. Wow, very exciting, very large audience again today. And I think it's worth to participate because we have an exciting talk ahead today. Before we start, let me make some remarks about the structure of the webinar. So the webinar is structured into two parts. The first part is the presentation part, where Dr. Hamm will present his presentation. During that time, please keep your video turned off all the time to not disturb him. And then in the second part, we will have time for your questions. You can make remarks, comments, whatever you like. And for that, we will use the raise your hand function in Zoom. I will explain that in more detail when we get there. You should see the first slide of Dr. Hamm's presentation. And additionally, on top of that, several small screens of participants. We recommend you to move your mouse to this second window and click the thick bar, which is the second button from the top left. And then you will only see the active speaker, and not much of the presentation will be blocked by the second window. And then you can move the window around as you like and see the presentation of Dr. Hamm. With that, I am at the end of my quick introduction. Again, enjoy today's webinar. Dr. Hamm, let me just make a few introductory remarks at the end. Dr. Hamm is the head of the Department of Bionic Lightweight Construction and Functional Morphology at the Alfred-Wegener-Institute. And he will talk today about the future of Bioinspired lightweight design. I'm looking forward a lot to this presentation, and I leave the floor now at the stage now for Christian Hamm. Thank you and enjoy.
Thank you, Bastian, and thank you, Janina, and hello, everybody. The core business of our institute, the Alfred-Wegener-Institute, is marine and polar research, especially in connection with climate research, models, and predictions. And here's to our ship and our colleagues who drift with the Arctic ice since October 2019. Understanding the dramatic climate change in marine and polar ecosystems is an extremely demanding and important task. But we are also proud that we can help to mitigate the dramatic rise of CO2 by developing sustainable lightweight solutions. This is also the reason why we are so happy to participate in the lightweight community. Now, where's the link to the lightweight community between the RV and us? Well, as you know, there is more in the oceans than whales. This image is not another logo of the LightCon, but a natural color capture of a phytoplankton bloom in the Barents Sea by the Sentinel-2A satellite. Phytoplankton are microscopic marine plants that have to drift near the surface of the sea since they rely on photosynthesis. And as a defense against predation, they often have biomineralized exoskeletons. The problem here is biominerals are very heavy, and according to Stokes' law, a heavily armored phytoplankton organism would rapidly sink to the seafloor. Thus, a heavy armor is not an option. It has to be as light as possible. And one of the reasons they actually need an armor is copepods, like this copepod, Calanus propinquus. There are huge masses around in the ocean. And the teeth of the copepods, the so-called mandibles, not only have a highly developed geometry of their feeding tools, but the material is also very advanced. The basic material is, as expected, chitin. You see it here in orange or red. And some of the edges have a silica cap in green, which is already very unusual. And in addition, there is resin in blue beneath the silica, which makes the mandible a very complex mechanical system. Now you will certainly wonder what kind of lightweight structures have evolved under these mechanical attacks. And here are some of them. What looks like the dreams of a production designer for a science fiction movie are actually radiolaria, unicellular amoeboid organisms which somehow manage to create silica structures which protect them from grazers. Not only the details, but also the general design of these structures are highly diverse. These radiolaria have been around for more than 500 million years. And if you increase the magnification of one of them, you see the most beautiful, smooth, and efficient transition from the long spines to a highly porous sphere you can imagine. Now the diatoms, the other large group we are investigating in German Kieselalgen, are similar in size. But unlike the radiolaria, they follow a common principle. Their general design is that of a petri dish or a camembert box. I don't know if you see it, but it looks like this. You have a diatom here, and it's organized like a box. But their diversity in the finer structures is even more extreme. And there are about 100,000 different species. And if you zoom in on the shell of a diatom, in this case Arachnodiscus, which is typically attacked from the rim, you see that it is reinforced by concentric and radial ribs, plus additional short ribs which cover local load cases, but do not have to extend into the middle. Also, the transition between the different structural elements are particularly smooth and seamless, which clearly prevents the occurrence of notch stress. Now, the material, we are not so far with the material, but we have indications that it is extremely important for the performance of these shells. And recently it has been found, for example, that the diatom silica is an extremely strong material. A team from Trondheim cut out a tiny beam and found out that the silica is about 10 times as strong as conventional steel. But in order to understand the whole structures and mechanisms behind the strength of the material, we need exact 3D data on the nanostructures within the shells. And we have an idea what they can do. They can create layers and spheres on the nanometer scales, even something like fibers, but we don't know exactly. But in total, they have the potential to create interesting composites. So we have access to about 100,000 lightweight structures, which have fantastic geometries we can study and understand in detail, and interesting high-performance materials where we still have to work on the methods to investigate them. Now, how can you transfer it into technology? And in order to use the potential of plankton structures for product development efficiently, we developed a systematic approach to use the natural structures and called it Evolutionary Light Structure Engineering, as an acronym ELISE. And here you see that the ELISE approach actually strongly resembles a conventional product development process. You need reliable technical specifications. Then you go into a conceptual phase, after which you create CAD proposals, which are evaluated via finite element analysis and then optimized. And finally, you create the final product. And there are about 17 or 16 different tools here, and it's very powerful, but also very time consuming. Now, what is different in the ELISE approach, it strongly resembles the conventional product development process, but it has 3 unique steps, which are based on natural principles. The first one is we use diverse natural lightweight principles to generate design concepts for each optimization. The second, we combine these design concepts as parametric CAD models with a rigorous optimization process, for instance, genetic algorithms. And the third is we use often multiple parallel optimization runs. So that comes from the natural approach and is different from the conventional process. And meanwhile, we have optimized many different structures using this method. The biggest one is a 50-meter offshore foundation for wind energy power plants. Now I have to skip the next one. So we had a lot of contact with the industries during all these projects and contract research. We found out that while all these collaborations were very successful and inspiring, most of them wanted to use the ELISE approach within their development departments. This was not practicable in our original approach, as we had this unusual combination of experts at RV consisting of biologists, biomimetics experts, and engineers. Plus, the process was really very complicated and time-consuming, thus only worthwhile for large development projects. It was not always explicitly mentioned, but it was clear that our partners wanted a software for lightweight optimization rather than giving us hundreds of orders for contract research. And actually, the first idea for software evolved about 8 years ago, and it was decided to start the development process for software. The start has something to do with interdisciplinary cooperation. This is, by the way, our exhibition at the Hanover Fair in 2012, when they pioneered the lightweight topic in Hall 6 already. At that time, we had a virtual Helmholtz Institute called Plankton Tech at RV, which was very interdisciplinary. And here, Jule Pohl of Pohl Architects developed a pavilion with fractal structures, which had a weight of only 700 kilograms, while measuring 5 × 6 meters, approximately. And she used the Voronoi function to create diverse, very variable versions of the same principle to adapt it to varying forms and sizes of the shell modules. You see the little modules in the pavilion there. And we found it very interesting because one of our main problems was also always to create versatile geometries, which are similar to the natural geometries, which are so complex. And then try to use this flexible approach to create our plankton geometries for lightweight solutions. And here you see the first results in 2D to generate and modify the honeycomb and rib construction of some diatoms. So it's already quite impressive. You see how versatile it is. Of course, at this stage it's only in 2D, so it's easier, or it was easier, but that was a really great start. There was also a thesis on that, and then after a while we had a nice project. In this project, a 2.5D version was developed. So you see actually these honeycomb structures which have a certain depth, which can be varied to different modifications. And this is a principle which is very similar to the building principles you find in diatoms, for instance. And finally, in the true 3D version, we got lattice structures, which could be modified to create a functional anisotropy in blue, or to smoothly incorporate double curved geometries here in green, which is not possible if you use unit cells, which are uniform, or to generate load-adapted structures using gradients within the lattice, as you see in the orange cube. Now, this was also interesting in connection with production methods. So this flexibility to generate complex lightweight solutions could now be used to consider the geometric restrictions of different production methods. And in this case study, it has been applied to sheet material forming in silver, or injection molding here in white, or for additive manufacturing in gray. So you have all these possibilities which can be adapted to the production method. And here you find a video where you see such a development process for an A-pillar. It was a development in cooperation with VW Osnabrück. And you already see that certain algorithms are used to generate and optimize the geometries of these forms, which was very helpful, and it was really a step forward to optimize and to flexibilize the production process, the product development process, sorry. Okay, so in the upper part, we had these honeycomb structures because they made sense here, and in the lower part you had branch figures and different sort of bionic features. And it was very interesting that this kind of development also led to very good crash tests. So they were much better than if you took conventional topology optimization. In the next video, you will see almost in real time an example how a setup for a bracket structure can be efficiently designed and readily modified if similar lightweight solutions are needed. So the individual steps for this setup are explained in the video. So I will not comment much during the next 3 minutes to avoid confusion. So please now concentrate on the process and the text. We seem to have a problem here. It stopped for some reason, and I don't see my mouse. So please hang on, I'll restart it. We stopped right here. You see this creating of the setup of a product development technical DNA. And you see now that there is a parameter study where different variations of the structure are tested for specific parameters, so that you get a whole array of diverse geometries. For instance, a model with a minimum mass, with a minimum support mass for additive manufacturing, and also with minimum overhang area. So this is a very powerful tool to create a setup and then be able to create all sorts of variation. And if you are, if it is necessary that you create a different bracket structure, which has a different footprint or different size or so, you can also use this setup. So this is really powerful. Still, this approach had some limitations, especially when it came to more complex structures. A lot of manual, time-consuming work was necessary. Because of that, 8 experts of our team decided to take the next step and to develop a completely new software within a startup, the ELISE GmbH, for a better and faster product design. And that is the logo, that is the new company. It features the first open software platform for a better and faster product design by automating the product development process. And here's how it works, and you see the philosophy behind it, under it. So you will have one user interface, which is a canvas where you do a sort of program, and a viewer where you see the structure, and underneath you see a set of different kernels and components. For instance, there is a different CAD kernel, a parasolid kernel included, which makes the construction, mesh generation, and optimization of solids much easier. That is where in the previous version there were some problems. It has also an own mesh kernel and a very efficient voxel kernel. It's really something new. Pre and post processing for FE analysis can be done directly in the ELISE software. And an optimization kernel which considers several methods is crucial for effective lightweight optimization. Finally, it is an open system which allows the incorporation of additional software modules via C# or Python interfaces. All these functions are integrated in one user interface. And such a software development is, of course, very demanding and can be only successful if you have very powerful, innovative partners in the beta phase. But as you can see, this is the case. But what is the advantage for product development of all these features? And here are some examples. You see that a lot of different functions and programs, so all these numerous, very diverse processes and programs have been integrated in the ELISE software, and this resulted in a much higher speed for the individual product developments. Instead of having to operate multiple programs and therefore user interfaces, it was possible to control almost all the processes within the ELISE system. Okay, now the next shows the ELISE team just before Corona, when they just moved to the new building. If you have specific questions concerning the ELISE software, don't ask me, ask these colleagues in the startup. They are not only of a very sunny disposition, they are also very competent. Okay, now it's hanging again. No, it's okay. Where is our present status? This is it. We've taken results from fundamental Planck research and have taken them as a basis to develop new technologies to improve the product development process for lightweight constructions. The technology has been patented, standardized with the Association of German Engineers, the VDE, and applied within numerous projects with major players of the automotive, the aerospace, and other industries. The ELISE GmbH was founded in 2018. At the same time, now new science topics with a high potential for technology transfer have taken shape. And in the last part of the lecture, I will show you what we are doing here. At AVI, we have implemented the task to study and transfer the new innovative lightweight features into the big research program Earth and Environment of the Hamm Society. And here we will investigate multifunctional lightweight solution using the new ELISE software, of course others as well, and publish the results. That's the standard for science institutes. But some of the results will end up as patents, as algorithms, or as software. And in those cases, we will include the new functions into the ELISE software via the C# or Python interfaces. And I will show you now 5 of our new projects for which we think such a scenario is likely. Okay, here you see the interface, that's the plan. The first is the project Good Vibrations. In this project, we use the structural principles of Plankton for cutting out vibrations in structural modeling of metal beams in a particle beam accelerator, which is currently planned to replace Petra 3 at the DAISY in Hamburg. And vibration control in general in lightweight products is very important, as vibration causes irritating noise, structural failure by fatigue, and many other problems. What we are doing is we use irregular Bioinspired lattice structures to define and optimize the vibration properties. And the results show that not only the eigenfrequencies, but also the damping factors can be manipulated. And the project will still run for a long time. Now, in the EU project OASIS, we are working with nanoparticle reinforced cast metal structures. And here we will use the ELISE approach to investigate robustness. So technical lightweight structures, such as the bracket and on the upper right side, you see the arrow maybe, are very performant when optimized by topology optimization. But at the same time, they are very susceptible to failure if unexpected loads occur. So natural structures are typically very versatile and therefore more robust. And you see in the lower right side, a structure inspired by natural principles, which is much more complex, and it showed very promising first results. Now, this is an unusual project, but have you ever noticed that well-constructed lightweight solutions are often very beautiful? We are just starting this new project, which is funded by the Weise Foundation, where we will systematically try to establish the connection between form, function, and aesthetics. The big question here is, do we just need certain degrees of symmetry and complexity to perceive something as aesthetic? Or does it also help if a lightweight construction is highly performant as a mechanical system? We have no idea yet, and apparently nobody has so far. So it's a risky project, but one we are really curious about ourselves. And I think the potential for transfer is also obvious. Anisotropy is also one thing which is very important. In the past, we have focused on structure only, on structure optimization, and mostly worked with isotropic materials such as plastic and metal. But natural materials are composites as a rule, and the performance of complex lightweight structures benefit if we can realize specific anisotropic properties for all parts of the structures. In the example at the right side, you see a model of arachnoidiscus, which is fixed at the rim and loaded in the middle. And as a result, you see the distribution of areas which experience tensile stress here in pink and compressive stress in blue. And if you zoom in at the lower right side, you can also see the directional stress tensors within the substructures. And what you get here is a combination of complex structures and a hint how fibers should be arranged if you can use highly anisotropic materials. In the LUFO project Fiona, which is going to start in October, this would be 3D printed carbon fiber composite. So a very interesting project when it comes to potential performance. And finally, morphogenesis is also very interesting, not only for fundamental research, but also for technology transfer. The diatoms produce their very impressive lightweight solutions by precipitation of silica from a solution via specific polypeptides. And the form is generated by a combination of active manipulation of the geometry of specific vesicles, the silica deposition vesicles, and self-organization processes such as phase separation. And if we understand these mechanisms and are able to use this knowledge to generate morphogenetic algorithms, we might be able to develop new morphogenetic software tools as well, which is very exciting, but still a long way. And we applied, we had a project on that where we manipulated the geometries using hypergravity. So we applied forces to the cytoskeleton system, but there's still a long way to go. Okay, who are we? That is difficult because we have a lot of transition. But now I want to thank the team. This is our team on the island of Sylt in 2017. About half of us is still at ARVI. The other half went to the startup. And we have 5 new members already who joined us. And a group picture of the new team on Helgoland is planned for the time after Corona. I hope you could get a glimpse on the potential and that there is a high potential in bio-inspired lightweight design and that it is worthwhile to dive deeply into research. But of course, the ultimate goal should be to revolutionize product development, thereby making the world lighter, more beautiful, more efficient, and to generate a sustainable balance between nature and technology. What you have seen today was mostly work in progress. Next year, we would be happy if you could join us to discuss the achievements and new developments in the lightweight community from face to face. So if you have time, of course, come visit us in Bremerhaven.